So this is lesson 8 for unit 4, and we're going to do just a one-day topic looking at something called linearizations. And with a fancy name like that, you would think that they would be really hard, but they're actually not. It's just a fancy name for nothing more than a tangent line approximation, where you begin your tangent line at some nice, convenient x value for your point of tangency. So we're going to try it out with this first example here. It says find the linearization of this function. Looks like it's a parabola, 3x squared plus 5. And the nice convenient place that we're going to pick up our tangent at is going to be at x is equal to 2. Sounds like a nice easy place to do that. So all I'm going to do off the start is just do nothing more than what we've done many times before. Find the equation of the tangent line. So I've got my original function here, right? It's this curved parabola. That's my f of x. And then I'm going to pick up my point of tangency at x is equal to 2. And I'm just going to try to figure out, what's going on with this tangent line that just skims by the graph at the point where x is equal to 2. Okay, doing what we've done many times, first thing I would do is just go and find the y value. And for that, I simply use the function. So hopefully I'm picking a nice convenient point to pick up the point of tangency. Now, I think x equals 2 would be great. So if I do f at 2, that's just going to be 3 times 2 squared plus a 5, and that ends up being 17. So I've got this point that's going to be on my tangent line here. The point is going to be 2, 17. And so yeah, that was a pretty convenient point to work with. It was pretty easy to find the y value. Well, now I want to go and find the slope for this tangent line, so I would go and do a derivative of my function. Okay, for that, the derivative would just be 6x. And generally speaking, if you've got a convenient point for finding a y value, you'll often have a very convenient point for finding the derivative. And now I'm going to go and do the derivative of this function at that nice convenient x value of 2. Geez, I don't even need a calculator here. 6 times 2, that's just going to be 12. So the slope of this line, for this tangent line right here, is going to be 12. Now, going and finding the equation of the tangent line, not all that hard. Okay, so let's go and find its equation right now. I'm just going to go y minus 17, all sitting on top of x minus 2, is equal to 12. Okay, so far so good. It's not quite a tangent line until I move that binomial up. Let's do that. So we would normally have stopped right here and said y minus 17 is equal to 12 times x minus 2. I'm going to go one more step. I'm going to move the 17, and I'm going to officially name this as some new function. How about I call it L of x, right? It's the line, the linearization, right? That's going to just be my y value for this tangent line, and it's going to be 17 plus 12 times x minus 2. Okay, half the battle's done. In fact, most of the work is done, right? We have this linearization. We know the equation of that tangent line. And there was a request up here. It says, oh, can you use this linearization, this tangent line that you found, to give yourself an estimate for the y value when x happens to be this rather inconvenient time of 2.3? I'm not excited about trying to put 2.3 into this function. That's not the easiest thing to do. Putting in simply a 2 was actually pretty easy. Didn't even need a calculator. Putting in 2.3 could be a little bit awkward. But maybe if I use the tangent line instead, 2.3 is really not all that far away from 2. 2.3 is right about here. And if we were just to go and find the y value of the tangent line, it's probably pretty close to being the y value of the function. And so that's the whole idea, is that now you can, as long as you're close to that point of tangency, you can estimate that function just by using the easier line. So here's the second part of the story. Let's try estimating that f of x, that blue curve. That's a bit complicated. I know a parabola is not all that complicated, but in general, this practice is great if you've got a very complicated function. And I'm just going to use that nice, gentle linearization, that tangent line, right? That L of x. So they're saying, oh, hey, could you go and give an estimate of the function at 2.3? And it's only going to be an estimate, so I'll put like a little wavy equal sign here, right? It's only going to be close. let's go and do the tangent line at 2.3. It's probably going to be pretty darn close. And the whole idea is that this tangent line that you've got right here might actually be so easy to work with that you don't even need a calculator. Let's try this out. So 17 plus 12 times 2.3, I'm just putting 2.3 in for x right here, minus the 2. Okay, maybe I can pull this off without a calculator. That would be 17 plus 12 times 0.3. Well, 12 times 3 would be 36. This is going to be 10 times smaller than that. So 17 plus 3.6. Oh, okay. 20.6. Now, that's just using the tangent line. It's not the exact value of the function, but I bet you it's pretty darn close. I'm going to try seeing what the actual value of the function is in just a second, but one thing to note is that because this graph in blue is concave up, the tangent's going to lie underneath it. So maybe worth a little note here, especially if we're going to go right now and see how close we were. I'm just going to throw a little thought in here. Since the function, the actual function, is concave up, the tangent line, if we're going to use that right as an estimator, it's going to be underneath it, so it will underestimate. The real answer. And let's just see how much it does underestimate it. I'm curious now, so I'm just going to take my calculator and see exactly what the function should have been. It was 3x squared plus 5, right? So 3 times 2.3 squared plus 5. A little more awkward. Can't do that easily in my head, but I bet you it's going to be pretty close to 20.6, 20.87. I'm not that far off, right? And that's the idea, is that this estimate using the linearization is going to be pretty darn close. Let's try that out with another function, also a little bit awkward, right? This square root here of x squared plus 9, and we're going to try picking up a nice point of tangency at -4 for x. Perfectly valid number to put into this this function that we've got there. So the first thing I'd probably do is go after the actual point. So I'd say, okay, well, what's the actual y value at -4? I'm hoping it's a pretty easy thing to do. So I'm going to have a -4 squared and then add 9. Okay, well, -4 squared would be a 16. Add 9 is 25. Oh, okay, well, I'm just going to be rooting 25. So y at -4 would just be a 5. Yeah, I didn't even need my calculator. That's kind of the whole idea, right? You should be trying to find some nice point to pick up your point of tangency. And I've got a good one. The point is going to be -4 and 5. Okay, next thing, the derivative. It's going to look a little messy, but if we've picked a nice x value to find the y, and we did, that -4 was pretty nice, it's probably going to be a nice x value for using this derivative too. Okay, I got this binomial to the 1/2, so the 1/2 comes down, x squared plus 9, all to the -1/2, then a little chain rule, 2x kicker comes out. Okay, let's see if we can go and actually drop in this -4. I'm only going to use this machine once, so I might as well just use it right here. I'm going to have that -4. Oh, this is really similar to what happened here. The -4 squared is 16, add 9 is 25. So I've got a 25, and it looks like it's getting flipped around and rooted. Okay, I can deal with that. And then 2, and then a -4. Well, actually, the 2 and the 1/2, they're just going to neutralize each other there. I've got a -4, and then I've got a 25 that's rooted to be a 5 and then flipped upside down. So I didn't even need to grab a calculator. I can see that this slope at that nice convenient x value of -4 looks like the slope is -4/5. Okay, so the equation of the tangent line, I'd be going y minus my my y value here, so -5, sitting on top of x minus my x value, so that's minus a -4, might as well say +4, is equal to -4/5. Okay, moving that x plus 4 up to the other side. I don't have a lot of room, so I'm going to do 2 steps at once. I'm going to call it L of x. I'm going to move that x plus 4 up and then toss the 5 over. So there's the 5 that was beside the y, and then plus negative 4/5 and x plus 4. Great. That is perhaps a little bit more convenient to use than that square root function. Okay, let's just take a look at what happened here in general to see if we can sort this out. For the last example we just did, we finished up with this linearization, which is, geez, it's just a tangent line, it's a straight line. And we ended up with 5 plus, we had this negative 4/5. I'm just going to start tearing this apart here. And then x minus the negative 4. Okay, so in general, it looks like the job of this negative 4/5, that's actually the slope for our tangent line. That's our dy dx. This x minus the negative 4, that part right there, when you do go to try out some numbers, right, where you're like, oh yeah, let's go and see if we can guess what the function would be at negative 4.2 or negative 3.85. This part here is going to show you the run, or what we simply call dx, right, the little shift in x. That's called a differential, right, that little shift in x. And if you take dx and multiply it by a dy dx, the dx differentials cancel, and this part right here in the linearization, that's actually finding your dy, okay, your y differential, how much the y's shift around as you move along this tangent line. Okay, if you want to write down a formula, and I don't even know whether it's a good idea because it's really so simple. You're just finding the equation of a tangent line. But if you want a formula, I guess here it is. The tangent line, right? You know, it's like some sort of y, right? Okay, well, where did this 5 come from? That was us actually figuring out the function at some nice, convenient x value, right? We said, oh yeah, let's go and find that at a, right? Some convenient spot. It's going to move this up just a touch. There we go. Then, moving down the road, we have this negative 4/5, that number. Well, where did that number come from? It's actually us figuring out the derivative at that really convenient x value. And then we multiply that by this binomial x minus the a. Okay, I'm just going to move that just a little bit, center things up here a bit. Okay, so that's, you know, if you want a general formula for figuring out the equation for the linearization. And this a that we're talking about is just some really convenient x value. In the example up above, it was negative 4. Negative 3 is maybe not as convenient. Negative 6 might not be as convenient for trying to do numbers in your head. But that negative 4 was quite nice. So just kind of commenting on, you know, where's this a coming from? It's some specific number, and that's just the, okay, lack of a better way to call it here, it's the nice x value where the tangent touches. You want to try to touch the graph at some nice, beautiful spot where you can do the numbers perhaps in your head. Okay, I'm going to use that linearization now to do some estimates for that function. I mean, that's a pretty crazy function if you look at it, right? It's got square roots in it, it's x squared plus 9, and I'm going to see if I can do this perhaps in my head. I'm going to do it twice and try to estimate the function at 2 spots, at 2 inconvenient spots, negative 4.2 and negative 3.85. So those are close to negative 4. I should be able to use this linearization and get pretty close to the right answer. So I'm going to use the tangent line, not the function. I can't put negative 4.2 in my head into that original function, but I can put it into here. This would be 5 plus negative 4/5 times negative 4.2 minus the negative 4. In other words, plus 4. I think we can pull this off without a calculator with a little bit of work, right? I've got my rise over run right here. That's my slope. And this part right there is going to be my run. And if I multiply my run by my rise over run, I'll find out what the rise, the differential, will be as I move away from that y value of 5. Okay, we got a 5, and then negative 4/5. What's this going to be? Negative 4.2 add 4. That'll be a negative 0.2. Okay, well, I've got to get some common ground here. Either go to fractions or go to decimals. I'm going to go to decimals. So this is 5 plus a negative 0.8 multiplied by a negative 0.2. Well, 2 times 8 would be a 16. And if they're both negative, it's still going to be a positive number. But it won't be 16. I have to move the decimal once and twice. So I've actually got 5 plus 0.16. It is doable to do that in your head, right? With a little bit of thinking, it can be done. And this is 5.16. Okay, I'm just curious to see how close I am. So I'm just going to play here for just a minute because I'm just kind of wanting to see how close we actually got. So I'm getting this 5.16. The actual answer, if I go with the original, oops, not here. If I go with the original function here, the square root of your x value, negative 4.2 squared, add 9. Okay, it's probably not going to be 5.16. Wow, that is really close. 5.16139. That's really, really close. I'm just going to play around here for a second. I'm going to store that, and I'm going to see how close I am. So I've got 5.16 minus that. Okay, I'm a little bit low, divided by what the number should have been, and then multiply by 100, because I want to think about this as a percentage. I'm like way better than 1% error. I'm minus 0.03% error. There's almost no error here, right? That's amazing. And I did it in my head, right? So we've got around decimal 0.03% error. That's remarkably good, considering that we did it in our head. Or let's try this other one out. What if we were to try out the linearization at negative 3.85? Okay, perhaps we can do this in our head. Maybe. I've got my original y value, and then here comes my dy dx. And then here comes my dx. How much is my run going to be? Negative 3.85. Well, you've seen what happens here. I've got minus the negative 4. In other words, add 4. Okay, so I have 5 plus, we already have seen that this is minus 0.8. We're going to head to decimals. And this, negative 3.85 plus 4 is 0.15. Okay. Can we do that in our head? You know, if you really work at it, you probably can do it in your head. Right? I've got this 5 plus, this is going to be negative 0.8 multiplied by a, let's split this up as a 0.1 and a 0.05. We'll do it separately. We can do it in our head. So we want 1/10 of this negative 0.8, so that's going to be negative 0.08, and then the 5. That is half as big as this 1. It's kind of like 5 is half as big as this 10, so the contribution from that will be half as big, minus 0.04. Okay, so I have to subtract 0.12 away from this 5. I can do this in my head if I really work at it. This is going to be 4.88. Okay, so we did that. Actually, it was a little bit of work, but we did it without using our calculator. Let's see how close we are, just for fun. So the actual function was the square root of your number, negative 3.85 squared, add 9. Like, there's no way you're going to do that in your head, right? And the actual number is, oh man, look how close that is, 4.88082 and some change there. Just going to store that, and I want to see how close I got. So I had 4.88 minus that. I'm just a little bit low. Okay, divided by the actual answer, multiplied by 100 to make it look nice. There's your percentage error. It's not 1%, it's decimal 0.1% error, right? Or 0.02% if we round up. So remarkably close, only 0.02% error, just by using this linearization. So that's all linearizations are. They're just tangent lines, but they're picking up at a nice, convenient x value. Don't try to do your point of tangency at negative 4.2 or 4.1. That'd be awful, right? Do it at negative 4, a nice place to work. Now, those 2 pages, they mark the end of the linearization notes, and I just thought since this lesson was really short, it might be time to throw in an AP exam practice question here. And this one is going to bring in some of our theorems, right? Just a chance to try them out. So totally switching gears, not really anything to do with linearizations. Just going to spend this extra time to try out one of these practices. So what does it say? Concert tickets went on sale at noon. They're going to call that time 0. And were sold out within 9 hours. Okay, so by 9 p.m. The number of people waiting in line, oop, little typo there. Sorry about that. It's probably in your notes too. The number of people waiting in line to purchase tickets at time t is modeled by, okay, so they're using some math to describe it, by twice differentiable function. So this means it's nice. It means you can do a couple of derivatives and nothing's going to go wrong. And that function goes from time 0, that would be noon, until 9 p.m., right? So that's all this is saying here. That's noon, and this would be 9 p.m. Values of the number of people in line at various times are shown in the table below. So this L, don't think of that as linearization. I know we just were using L for that. That just means people in the lineup. And they've given you some discrete values. 1, 2, 3, 4, 5, 6, 7 different values for the number of people in line at different times. Looks like by 9 p.m. there was nobody left in line. Okay, part A. This part's not too bad. Use the data in the table to estimate the rate at which the number of people in line was changing at 5:30, okay, at time 5.5. Well, that is stuck somewhere right in between these 2 columns in the table. Show computations that lead to your answer and include some units. Well, when they say the rate, right, they're talking about the slope of the graph. Okay, that's what they want. Now, in the actual AP exam, they did not give you a graph, but I've just included a little graph here. So we could go and just kind of plot the points that we've got here, just to kind of get comfortable with the story. So I'm just going to put them in. At time 0, at noon, we had 120 people in line. Okay, that'd be about there. Time 1, there's 156. That puts us about here. Time 3, 176. That would be right up about there. And time 4, 126. Okay, so somewhere around there. Then we're going to jump all the way to time 7. We're going way down the road. And at time 7, there are 150 people in line. And then at time 8, there are 80. Okay, there's 75, there's 80. And then at time 9, nobody left in line. Now, they're only giving us just those 7 points. That's it. And they're saying, well, the function that's there, you know, it's twice differentiable. It's going to be very smooth looking, and it's going to hit all of those points. And they're saying, well, what do you think the slope of this graph would be at 5.5? Like right here, there's just like what's going on there? There's no picture there. Well, the best we can do for our estimate of the slope of that graph at 5.5 would be to actually do the slope between the 2 points that are right nearby. So let's go and look from 4 up to 7. That's the closest that we can work with to try to figure out our slope here. It's all we've got. And so we're going to do nothing more than a little grade 10 slope calculation here. We're going to do this. Okay, just grabbing the numbers that I have, a y value of 150 minus a y value of 126 all over 7 minus 4. I think this was actually a no calculator question too, so I should be able to do this without a calculator. 24 and 3 looks like positive 8, and the units, just looking at what we're working with here, we've got people for L, right? It tells me that the units are people there, and then we've got hours there. So this is people per hour. So my best estimate is that the line is actually growing at about 8 people per hour at that moment. It's just an estimate, but that's the best I can do. Okay, part A wasn't too bad. Now, part B is tough. We've got to really be on our game in order to get this to work. It says from 0 to 9 for time, from noon until 9 p.m., what do you think is the fewest number of times at which the slope of this graph must be 0? That's what that says, right? L is the graph we've got, L prime is its slope. What is the fewest number of times that the slope is 0? Do not fall into this trap. Just because you can see with this point that that's the highest point they give you, do not think that because that's the highest point that you can see, that that is the peak of the graph. We do not know that that's true. All we know is that this graph is really smooth. It's twice differentiable, so it's got a derivative and even a second derivative. But it is totally possible that this is a minimum. Maybe the graph goes up really high and then smoothly comes down and then goes back up. We don't know how many times this thing goes up and down. All we know is that it does hit all of these points that are there. So I'm not going to assume that I've got a maximum there at time 3, right, and a minimum at time 4, and a max at 7. I just don't know that that's true. But I am going to, just to kind of get comfortable with this, draw in what I think might be a smooth kind of fit to this story. And there might be maximums, near 3. Maybe it goes like this. Maybe it kind of goes up, peaks around here, comes down, maybe has its minimum, I don't know, somewhere in here, and then, I don't know, maybe it goes up and then comes down like that. So just eyeballing it from this little sketch I've done, I'm suspicious that there might be 3 times at least where this graph has to be flat in order for this to work. But now I have to go and prove this, and I have no proof that the graph is going to look like the green one that I've got. All I know is that it's smooth. Okay, that's it. Okay, well, let me just erase this green line because I don't know that it's true. And we'll get ready to go. Here is one way that you can actually prove that this graph does have 3 flat spots, at least 3 flat spots. First thing I'm going to do is just point out that this thing is twice differentiable. So if that's the case, then I know that L is continuous and differentiable. Because they said I can take 2 derivatives, so L has to be at least continuous. And I also know that L prime, it's going to exist because they said it's differentiable, in fact twice differentiable. So L prime is going to have to be continuous and differentiable. That way I can take another derivative and I get to L double prime. So L double prime has to exist, right? It's there. I suspect that it's going to be a beautifully continuous function as well, although that might be open to some debate. Okay, well, they gave me a bit of a hint when I did part A. They said, hey, what do you think about the slope there on average, or at 5.5 for time? What do you think this is going to be? And I averaged the slope out and said, well, on average from 4 to 7 for time, looks like the slope on average has to be 8. That means that somewhere inside this story between 4 and 7 for time, there has to be some moment where the slope is going to for sure be 8. I don't know exactly where, but somewhere in there. That's just the mean value theorem that says that that's going to happen for sure. So I'm just going to drop a little arrow randomly in here just for a second. And I know that there's going to be some x value. I could call it, or t value. I could call it c, where I'm going to get that slope of 8. Well, let's actually examine a few other spots here that could be handy. Like, hey, what about here? Where I've got, looks like on average, a positive slope. I could go and find its value. And then it looks like the slope goes negative on average, right? Then it goes positive again, and then it's going to go negative again. Maybe I can go and check in here. So I'm just doing some average slopes. Okay, that's all I'm doing. But I'm going to fire up the mean value theorem, so I'm kind of keen on this idea of average slopes. The average slope here, we already found, was positive 8. let's go and check out some of these other slopes, these average slopes. Hey, from 1 to 3, a little 2-hour run. Looking at the data table, okay, as we go and examine that, from 1 to 3, these values, they go up by 20, right? 20 more people are in line over a 2-hour period. On average, that is a positive 10 for its slope. And then from 3 to 4, whoa, a drop of 50, and it happens in 1 hour. So the average slope here is minus 50, okay, for the average slope. Then from 7 to 8, we drop by 70 people in 1 hour. So the average slope here is minus 70. Okay, it's time to start talking about this mean value theorem. The mean value theorem says, since this graph is beautifully continuous and differentiable, that somewhere between 1 and 3, I don't know where, but somewhere between 1 and 3, there is a C value where the slope would actually be 10. And the mean value theorem again says somewhere between 3 and 4, I don't know where, but somewhere in there, there's a C value where the slope has to be negative 50. And then in here, somewhere there's a C. We've got a lot of C values. And one here, why don't we start clarifying these? Why don't we call this C1, C2, C3, C4. And so what you could do is you could say, hey, look, 4 times I'm going to do this mean value theorem. So this might be maybe the first thing that I would do. Say, okay, mean value theorem, 4 times. 4 times I'm going to deploy it. I've got a function that's continuous and differentiable, so the mean value theorem is fair game, right? It's time to talk about that. We could say at some C1, and that C1 is stuck in between 1 and 3, right? So 1 is less than or equal to C1, less than or equal to 3. At some spot right there, L prime has to equal positive 10. And continuing on, doing this 4 times, at some C2, stuck in between 3 and 4, I know that the slope of that graph has to be negative 50. A couple more times. At some C3, that's in between 4. So they gave me a bit of a clue, right, when they forced me to do this one. Between 4 and 7, at some spot in there, the derivative has to be positive 8. And then at some C4, between 7 and 8, that derivative has to be negative 70. Okay, well, I'm halfway done. So far I know that if I was to look at the graph of L prime, if I did draw it, they've told me that this original picture was twice differentiable. So if I was to draw a graph of L, actually let me just move my axis here a little bit. If I was to draw a graph of L prime, I know that it has to be beautiful as well. Because they said, oh, you can do 2 derivatives and you're totally okay. So here's time, here's L prime, and I've got some spots here. I don't know where exactly C1 is, but it's between 1 and 3. So there's a C1, a C2, a C3, and a C4. And at that C1, I'm not exactly sure where it is, but it's between 1 and 3. I know that the L prime graph is up there at 10. And then at C2, it's down here at negative 50. Okay, it's going to have to go through 0. And at C3, we're back up to 8. And at C4, we're down to minus 70. So we're going to have to be crossing and hitting 0 at a few spots. Somewhere in here, and somewhere in there. In between C1 and C2, C2 and C3, and C3 and C4. I don't really know where C1 and C2 and C3 and C4 are, but I know that they're in that order. And I'm going to now call these points, I need a new letter. Let's call them like D1, D2, and D3. And so I'm now actually going to do the intermediate value theorem. I'm going to do it 3 times. I know that that L prime is perfectly fair for doing the intermediate value theorem. That L prime has to be continuous. So this is fair. I could say, hey, at some D1 that's stuck in between C1 and C2. So C1 less than or equal to D1 less than or equal to C2. Actually, it wouldn't even be equal. It's got to be strict inequalities here, because at C1 I know that the slope for L was 10, right? And then the slope for L was negative 50. So it's not at those moments. It's in between. At some spot there, if you were to check out L prime at D1, you're going to get 0. It's an intermediate value in between 10 and negative 50. And then we're going to play the game 2 more times, and then we're done. So this is in between C2 and C3, and then in between C3 and C4. And so I'm ready to say, yep, I think I've proved this here. We've got at least, maybe more, but at least 3 times. Right? And that's what it's going to take to prove that. You have to use the mean value theorem and then the intermediate value theorem multiple times in order to get it to work. Just thought it'd be kind of a nice time to try practicing one of those theorem questions, and that's going to wrap up our lesson here for today. And then the next 3 lessons are about something called related rates.